All right, first we're going to start on number 22. We have to go back and make a correction because Mr. Cummings had a boo-boo on number 19. And yes, 4a times 2a to the square. 4 times 2 is not 4, as it turns out. It is 8, as my incredibly smart students noticed, and I did not. So that's a correction. So if you were noticing that on the last particular question, you are right to notice that. Yes.
On number 18, why is it x to the 9th?
The question was, why is it x to the 9th on the bottom of number 18? Is because of the quotient rule, which says you subtract the exponents of like bases, right? So what is 1? So it's going to be x to the 1 minus 8. So 1 minus 8 is...
But shouldn't it be negative 8 minus 1?
It could, but then negative 8 minus 1 is going to be negative 9, but where? So yeah, you could have x to the negative 9th on the top, at which point in time I would kick those down to the bottom. Or I could have x to the positive 9 on the bottom, in which case I would be absolutely done already. Cleared up on that? Okay, good question. Moving on to number 22. 21. I guess 21 does come before 22. Oh yeah, 22. When we're adding and subtracting monomials, we're looking for like terms and like terms only. And when I do that, I find the like terms are 6x and negative 8x. They'll combine to make negative 2x. And negative 7x cubed and negative 3x cubed combine to make negative 10x cubed. I don't do anything with the exponents. I very simply just add the coefficients. We've been doing that for a couple units now, but it does get a little confusing when you have all these other rules when you're multiplying and raising things to powers. Yes, question?
I did
negative 10x cubed minus 2x is absolutely correct. The commutative property applies here. This could also be negative 10x cubed minus 2x. You could also have plus negative 10x cubed or plus negative. As long as you have a 10x cubed that's negative and a negative 2x, you're good to go. 22, we have a power outside of parentheses. We have to multiply it by each power on the inside. Doesn't matter if they're X, Y, Z, smiley faces, peace signs, hashtags, does not matter. Okay, what those things are. If they are bases with exponents, you multiply. So it's 10 to the 3 times 4 is 12 times 7 to the 12. Now the question ultimately will be, Mr. Cummings, do you want us to figure out what that number is? And the answer is no. Okay, 10 to the 12th is in the trillions. 7 to the 12th is in some, I don't care. No, it's not, it's unreasonable to ask you guys to do that. Now, people have asked, okay, if this is 10 to the 12th times 7 to the 12th, is that the same thing as 70 to the 12th power? Question mark, question mark. And it actually is. It actually is. Because if I basically reverse the power rule, this would be the same thing as 10 times 7 to the 12th power again. But I wasn't expecting you guys to do that. 10 to the 12th times 7 to the 12th. Yep, because it is right.
Don't we add like the 2000?
No, those are not the same basis. Those are not the same basis, so we cannot add those two things together. We have to leave it just like that. So my highlighted answer there is the best one. Highlighted answer is the best. Next one, another power rule one. That's going to be 4 to the 3rd, which it's not unreasonable to evaluate 4 to the 3rd, n to the 12th, m to the 3rd. And 4 to the 3rd is, what is 4 to the 3rd? 64. 64 n to the 12th. M to the 3rd. Everybody okay there?
Yep.
Moving on to scientific notation, we have to make a coefficient that is between 1 and 10. In this case, it is going to be 7.03. Now let's figure out how many times I'm going to have to move that decimal place, and that's going to be the exponent of my power of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. but in the positive or negative direction? Negative. This is a very small number. Incredibly microscopically small number. 7.03 times 10 to the negative 11. The next one I have, this is millions, billions, 340 trillion. So let's put that in scientific notation. The coefficient's going to be 3.4 times 10 to the, how many times will I have to move my decimal place, which is currently here and invisible? How many times will I have to move it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times. In standard notation, I have to go back the other way. Once again, the exponent tells us how many times I move my decimal place. So I start off with 1.09, and I'm going to have to move it 8 times. And is this a big number or a small number? Small number, so I'm going to have to move it to the left. 1, 2, 3, 4, 5, 6, 7, 8. There's my new decimal place. 1, 2, 3, 4, 5, 6, 7 zeros. Then 109 is your correct answer. 0.7 zeros, then 109. On the next one, is this a big number or a small number? 5.6 times 10 to the 7. I have to move that decimal place 7 times, so that's going to be 5, 6, and then 6 zeros afterwards. You can add your commas as necessary, and that is 56 million. Question? No, I will not count it wrong if you do not put commas, but no, that's the same number. Okay. Number 28, we are computing in scientific notation, and sorry for these X's that have no spaces by them. They meant it to indicate some multiplication, but I have to use the product rule. 4.5 times 2 is 9. Times 10 to the 5 plus 7 is 12. 9 times 10 to the 12.
Well, it looks the same thing.
I know. Right. Okay, and quotient rule on the next one, 6 divide 3 is 2. 10 to the 6 over 10 to the 4. 6 minus 4 is 2. So this is just 10 to the second, which is 200. 2 times 10 to the second is 200. 30, it asks you to explain the rules. So you have to be the teacher. If you were to explain the rules for adding and subtracting monomials, what would you do? Yes. Sure. And I'll stop this for now.